Hello friends, I welcome you in lecture number 31 on group theory. In this lecture, we will discuss this question which was asked in GTU Summer 2020 exam. The question is, show that G with addition modulo 5 is a cyclic group where G equal to 0, 1, 2, 3, 4. So as we recall that this set G is given under addition modulo 5. So this set G has elements which are equivalence classes. Okay, the elements are not integers, elements are the equivalence classes generated by 0, 1, 2, 3 and 4. So be careful about these different notations. Some authors are simply writing 0, 1, 2, 3 and 4, but this is the correct way of writing this set G, which is the set of equivalence classes. And we have discussed about all this addition modulo and modulo group in lecture number 7. If you have not seen that lecture number 7, I suggest you to watch that lecture number 7 first before going for this lecture. And we recall that this operation addition modulo 5 is the operation between two equivalence classes and is defined as, if I consider two equivalence classes generated by A and B, and if I apply this binary operation addition modulo 5, then here we will write the equivalence class generated by remainder when this A plus B is divided by 5. So this is the way how this addition modulo works. So resulting element is the equivalence class. Here A and B can take the values 0, 1, 2, 3 and 4. Now we are asked to prove that this set G is a cyclic group under this addition modulo 5. So for that we recall the definition of cyclic group. We know that a group G under binary operation star is cyclic if for some element of group, suppose I consider element A in group G, if for some element A in G, every element of G, if we take any element X in G, then we can represent X as A to the power n for some integer n, for some n belongs to Z. Here A raised to n means we have to consider A star and so on up to A n times. So be careful, this is not simply multiplication. A raised to n means it is the notation for this A star A n times. If I have addition operation, then A raised to n will be equal to A plus A and so on up to last term A n times. So this is going to be n times A. If it is multiplication, then it is A raised to n will be equal to A into A n times. Here our operation is addition modulo 5. So A raised to n means A addition modulo 5, A addition modulo 5 and so on, A addition modulo 5 n times. So that is the meaning of A raised to n. So if we take any element of group G, and if every element can be represented by some fixed power of this element, fixed element A, then we can say that group G is cyclic. So if we want to prove that our group is cyclic, we have to show at least one element that is fixed element. We have to find out some fixed element in group G such that every other element of given group G can be represented by X equal to A raised to n for some n integer. Here our group is the set of equivalence classes So we have to decide that we can find out whether we can find out some element out of this such that every element can be represented as power of that fixed element. So we can start with equivalence class generated by 1. Suppose we consider equivalence class generated by 1, and if we find out first power of 1, then we will obtain here 1 because it is single power. So we can say that we have written 1 as power of 1. Now suppose we consider second power of 1, then let's see what we obtain. So this is 1 raised to 2, that means we have to consider equivalence class 1 with itself, and we have to apply addition modulo 5. This is equal to remainder when 1 plus 1 is divided by 5, that is 1 plus 1 modulo 5, that is 2 modulo 5. So we have to decide what is the remainder when 2 is divided by 5, and we know that 2 is less than 5, so 2 will be the remainder. So therefore we observe that 2 can be represented as second power of equivalence class 1. Similarly, we can check for higher powers, and we see that whether we can obtain every other element as a power of 1 or not. So now I try for this. This I can rewrite as 1 square addition modulo 5 1. Now 1 square is nothing but 2, so here we replace it by 2. 2 addition modulo 5 1, and this is going to be 2 plus 1, that is 3 modulo 5. So we have to write the remainder when 3 is divided by 5, and because 3 is less than 5, remainder will be 3. So we have written 3 as third power of equivalence class 1. Equivalence class 3 can be represented as equivalence class 1 raised to 3. Similarly, we try for fourth power of equivalence class 1, and be careful, here our operation is addition modulo 5. This we can rewrite in this way. Now we replace 1 raised to 3 by 3, equivalence class generated by 3. So this is equal to 3 plus 1, that is 4 modulo 5, and remainder will be 4 because 4 is less than 5. So 4 is also expressed as fourth power of equivalence class generated by 1, and we have only 4 elements. Now what about 0? We must generate 0 also. So for that we can try for fifth power of equivalence class 1. So this we can rewrite as fourth power equivalence class 1 addition modulo 5. This is equivalence class generated by 4, and equivalence class generated by 1, that is 5 modulo 5. 4 plus 1, that is 5. So we have to find out the remainder when 5 is divided by 5, and we know that remainder when 5 is divided by 5 is 0. So 0 is also written as fifth power of 1. So therefore we can observe that every element of given set can be written as some power of this fixed element 1. 0 is written as 1 raised to 5, 1 is written as 1 raised to 1, 2 is written as 1 raised to 2, 3 is written as 1 raised to 3, and 4 is written as 1 raised to 4. So therefore we can say that every element is represented in power of 1. If we take any equivalence class in a group G, then we can write it in this form: 1 raised to n for some integer n. Therefore this is a cyclic group, and this 1 is called the generator of this group. Now you may have question that why I started with 1. So because I know that if I have addition modulo n, then it is always a cyclic group. For any natural number m, Zm under addition modulo 5 is a cyclic group with generator equivalence class 1. Therefore I started by 1 directly. But if you are not sure, you can start randomly. You can start with 0. Suppose I start with 0, then I cannot write every element as a power of 0. For example, if I take 0 raised to n, then I will always get this is equal to 0. I will never get other element. So I cannot represent every element as a power of 0. Suppose I am trying for 2, then if we take first power of 2, then we will obtain 2. Suppose we consider second power of 2, that is 2 addition modulo 5 2. So this is going to be 4 modulo 5. 2 plus 2, that is 4 modulo 5, and remainder when 4 is divided by 5 is 4. Now suppose we increase the power of 2, this is square of 2 addition modulo 5 2, and this we can replace by 4. So here we obtain 4, and we replace 2 square by 4 plus 2. Now 4 plus 2, that is 6. So we have to decide 6 modulo 5, that is remainder when 6 is divided by 5 is 1. So 1 is written as third power of 2. Now we check for fourth power of 2. This is equal to 2 raised to 3 addition modulo 5 2. 2 raised to 3 we have obtained is 1, and addition modulo 5 2. So this is going to be 1 plus 2 3 modulo 5, and remainder when 3 is divided by 5 is 3, because 3 is less than 5. Now what about 2 raised to 5? So that is going to be 2 raised to 4 plus 2, and I directly replace 2 raised to 4 by 3 and plus 2. This is going to be 3 plus 2 5 modulo 5. Therefore this is equal to 0. Remainder when 5 is divided by 5 is 0. So we can see here that 0 is written as fifth power of 2, 3 is written as fourth power of 2, 1 is written as third power of 2, 2 is written as first power of 2, and 4 is also written as a power of 2. So we can check this is 0, 1, 2, 3 and 4. So you can show that every element of given group can be written as some power of 2. So you can show for this element 2 also. So 2 is another generator of given group. So it is not necessary that you should start with 1 only, but remember that this group is always cyclic and 1 is always the generator. You can have other elements as its generator also. A cyclic group may have more than one generators, but if we have Zm, that is 0, 1, 2 up to m minus 1, then we can remember that this group is always cyclic under addition modulo m, and 1 is the generator. We can always express every element of this group as a power of n for some integer n. Therefore I started by taking different powers of 1, and we observe that this 2 is also working as generator. So you can write for 2 also. You should show the existence of at least one generator. So here we can see that therefore 1 raised to n equal to this for every a equal to 0, 1, 2, 3 and 4. Therefore, G with addition modulo 5 is cyclic group. And if you are taking 2, then you can write in this way. Every element can be written as some fixed power of 2 for every a equal to 0, 1, 2, 3 and 4. Therefore, G with addition modulo 5 is cyclic. So you have to show at least one generator. Your cyclic group may have more than one generators also, and here we observe that this is a cyclic group and it has 1 and 2 as generators. Now if they are using this type of notations 0, 1, 2, 3, 4, then you can simply write in this way also. Okay, that is also correct. 1 raised to 1 equal to 1. You can write that 1 raised to 2 equal to 1 addition modulo 5 1, that is 2. But be sure that whenever I am writing this, I must have in my mind that this is not power of integer 1, it is the equivalence class generated by 1. So be careful and don't confuse between these two notations. If they are writing equivalence classes here, then you should write equivalence classes only. If they are writing only 1, 2, 3, 4, then you can ignore these brackets which are used for equivalence classes. But you must be clear that this G is the group of equivalence classes generated by 0, 1, 2, 3 and 4, and this operation is between equivalence classes, not between integers. Here there is a big difference. This is not operation between two integers, it is the operation between two sets which are equivalence classes, and resulting element is also a set which is the equivalence class generated by this remainder when a plus b is divided by 5. So they can ask you to prove that this type of group is a cyclic group, and you can remember this note that for any natural number m, Zm under addition modulo m is a cyclic group with generator equivalence class generated by 1. So that will reduce your work. You don't have to search for generator. You can directly start with powers of 1 and you can represent every element of Zm as a power of 1. So this is all about this session. I hope you will be able to do this type of problems. Thank you.